Yes, class. Thank you once again for joining us. Professor Yellow Ted was just giving me my final instructions as to how to explain this one to you, boys and girls. So do pay attention. Fold your legs, cross your arms the other way around if you like. Stop throwing those paper darts and pay attention. This is very important. Today, gravitational redshift. So, to understand gravitational redshift, I need to take you on a little journey. So do bear with me. Stick around until the end. You'll get it at the end, I hope. But I want to give you some background information that you are going to need in order to understand this material. So here it goes. In the late 1600s or so, a chap by the name of Sir Isaac Newton came up with a law, which we'll put up on the screen there. Basically, Newton said P equals mv, where P is the momentum. This really comes from what is these days referred to as Newton's zeroth law. Newton never actually said this. He just assumed it to be so, self-evidently so. He had no reason in his mind to think on it otherwise. But he assumed that mass was a conserved thing. Conservation of mass. Chemists use it all day, every day. To all intents and purposes, the idea that mass is conserved is fine and dandy. It doesn't get in the way of getting things scientifically correct and making correct observations, correct predictions of all sorts of crazy things like eclipses of the moon and eclipses of the sun and the transits of planets and the passage of seasons and those kind of things. Works pretty well to all intents and purposes for all that kind of stuff. Anyway, there we go. Momentum is a product of the mass, the physical stuff, multiplied by its velocity. There you go. That's what Newton said. And as I say, to all intents and purposes, quite rightly so. It wasn't until around 1905 when another chap came along by the name of Einstein, and he is credited with having said E equals mc squared. It's probably the most famous sum that you'll ever see written anywhere at any time. It's kind of become the thing, hasn't it, in terms of all of that. Only Einstein actually didn't publish that. That equation doesn't actually occur anywhere in the article to which it's attributed. Einstein actually wrote something a bit different in terms of what the subject of his equation was, and his meaning was quite clear, as it turns out, on further inspection, actually. And we'll have a bit of a look at that in a moment. Anyway, Einstein said E equals mc squared, which implies a number of things, including, but not limited to, that there is some kind of mass-energy equivalence. There is some kind of interchangeability. It turns out that we need to think about mass as a form of energy, and mass is not immutable and conserved in the way that it was thought about by Newton since about 1600. Really, it turns out that you can convert an amount of matter, stuff, into energy, and that was shown on what was first really shown to devastating effect on the 6th of August 1945. This guy wasn't the sole guy involved in making that happen, but this guy is one of the most famous physicists, I guess, of our time, really, or close to our time. This is Richard Feynman, who is credited with many things in physics, including he was a leading hand in the development of that device that was used on that morning in Japan. He's also the bloke who diagnosed what went wrong with the shuttle explosion as per the O-ring. That was him as well. And he's also the guy who put together Feynman diagrams and is credited with having developed much of quantum electrodynamics. So there you go. That's him. Clever cookie. So he was involved in the clear demonstration of what Einstein had proposed in 1905. Of course, Einstein was mortified that his realization of that equivalence had been used in that manner. Of course, he thought it was a terrible thing, obviously. Anyway, so pretty much we know that mass is not conserved. It is, you can convert mass to energy, and obviously energy to mass as well. Energy and mass, there is an equivalence. Mass should be thought of as one of the forms of energy. Why is that relevant to any of this redshift stuff? Well, let's just cover my girl Emily first, because she's one of my faves. So we'll just pop Dr. Feynman into the background there. Let's talk about Emmy Noether. Yes, I think personally that she is one of the most incredible mathematicians who pretty much has ever lived. Much of the work in physics since her time actually stands squarely on her shoulders. She is the one who came up with Noether's theorem, and that is the one that tells us about symmetry and conservation, the relationship between those things in the objective reality in which we find ourselves, and how we can predict which things are conserved or not conserved as per symmetry rules. If you'd like to see a video on symmetry, etc., then do comment below here and say, yes, make us that video. But in the meantime, take it as read. Brilliant mathematician. Came up with Noether's theorem, showed the relationship between symmetry and conservation. And anyway, she basically said unto us, that the things that are conserved are both linear and angular momentum and energy, but not mass. And she said so in 1915 was when her theorem was published, i.e. mass is not conserved. Since Noether's time, with some of the physics that's been built on her work, other things have been added to the list of conserved things, and they would be things like gauge symmetry, really. So you have a conservation of electric charge, weak nuclear charge, color charge, etc. Those kind of things. They've all been confirmed since experimentally. So we have to add gauge to our list of conserved outputs. So there we go. We do so joyfully, and we say thank you very much, Emily. I don't think Emily gets enough big ups, frankly, in the mathematics world for what it is that she was able to achieve. Anyway, that's Emily. That's what she did. That's what most of physics is built upon. She really is the mother of modern physics, actually, in my opinion, ahead of some of these other characters. I think she stands, equal shoulder to shoulder with Einstein, frankly. But that's just my opinion. So there you go. That's Emmy Noether. Bye, Emily. So how is any of all of that relevant to redshift? Well, here we go. When you look at the appropriate sum for describing the energy which is clearly contained within what we sometimes parsimoniously describe as a photon of light, a quanta of light, we see that the sum, which is on the screen now, of course, is E squared is equal to m squared c to the fourth power plus p squared c squared. Okay, so E is the energy, which we know is a conserved variable. Mass is m, not conserved, so that's the thing that can vary. C, the speed of light, absolutely and utterly fixed and inviolate and seen as the same thing from every inertial frame and agreed upon as such. So a constant, absolutely. And P stands in this case for momentum of said, say, photon of light. So if you look at that sum there on the screen, if a thing, let's imagine it's not a photon for a moment, but it's a thing of mass, a solid thing, if that thing is not moving as per our initial frame of reference, then that sum reduces to E is equal to mc squared. Interesting. However, if the thing is not massive, let's say it's a photon, which has no mass, then that sum actually reduces in that case to, well, E is equal to PC, or another way of looking at that would be P is equal to E divided by C. So we have a special case whereby we describe the energy of a photon. Why do we describe the energy of a photon? Well, because if a photon is allowed to interact with another body, it will affect that body. There is a momentum to be passed on, and we can see that with all sorts of experiments with light turning motors and all of that kind of thing. Yes, and or light knocking electrons out of metallic plates and causing voltage, and those kind of things. Light definitely does have an impact. It does interact with matter, whether or not it is indeed comprised of any kind of matter itself, which we're told it isn't, and there's no reason to argue with that, other than our own obsession, really, with our insistence on reality being contingent upon being in possession of an amount of matter, an amount of mass. I don't know, other than Newton's zeroth false law, why we would be so enamored of that. I guess it's in our daily experience. Those of us that aren't causing nuclear explosions to occur regularly, pretty much we don't deal with matter doing anything except being conserved to all intents and purposes for what we're doing. So we insist upon it. Basically, the momentum of a photon can be thought of as unchanging by some people. They'll say, "Oh, its momentum never changes," which is an interesting point we'll get to a bit later on. In this case, the energy of a photon, which has no mass, is defined as being something relative to our absolute frame of reference, which is C. C is the only frame of reference we have. It's the only thing about which we will absolutely agree, irrespective of our inertial frame. So our absolute frame has to be C, really. So let's say that the momentum doesn't change of the photon. and its value is equal to hf over c squared, where h is Planck's constant and f is the frequency of oscillation of the photonic field from positive to negative and back, or from negative to positive and back. One wavelength is what I'm saying. How many of those occur in a second? That's the frequency of the light. Planck's constant is a number given to us by Max Planck. So yes, Max Planck. There's Max. Hello, Max. Good to see you. Max Planck gave us a number for Planck's constant in 1900. What is Planck's constant? It's a quantum of action, apparently. It has a number, and it is 6.62607,004 times 10 to the power negative 34 square meters per kilogram per second, basically, or if you like, joules per second. And for those that want to work in electron volts, 1 joule per second is equivalent to 6.242 times 10 to the power 18 electron volts per second. Okay, so there you go. The energy of the photon is being defined in the case of what is the energy of the photon. It is stepping away from the Newtonian requirement that momentum energy requires some mass. It's a relativistic way of looking at it, I guess. However, that brings us to gravitational redshift, where we're told, by Max, thank you for dropping in, we are told that what happens when a light beam, a photon, has to climb out of a gravitational well, that causes a red shift, because that photon is losing energy, fighting against the force of gravity. And that's one interpretation. That's a particle-based interpretation. It's basically, well, let's put the sum up on the board for fun. Some people are so desperate for anything that has energy to have mass that they impose a thing on a massless photon called its relative mass. And basically they're saying that the mass at rest squared times c to the fourth power plus p squared c squared is equal to the relative mass squared times c to the fourth power. And the relative mass is defined basically as hf over c squared. So that's how that's spoken about in terms of the accounting for energy and stuff, and that sort of fits in with the particle interpretation of a photon. But I think that's probably intellectually quite messy. It raises a lot of questions for people. I think that's hard to understand. I don't think we really need to go there, actually. I think we can describe gravitational red shift in a much more accessible manner. And that was the reason I wanted to make this video. So that's all the preamble that I'm going to give you. Let's go now to another perspective. Well, really, there are three perspectives I want to talk to you about. The model I'm going to show you is a model of a wave of light. In the first instance, I'm going to show it to you coming from some point in space towards another point of reference, which is going to be the Earth, spoiler. And we're going to see what happens to that ray of light, that photon. And we'll talk about that a bit, and then I'll show you some other stuff. So let's go and have a look at situation A, where we have said light beam going towards Earth. So Here it is here. As you see, it started out red and it steadily gets more orange and more yellow. And then we start to see the greens, and then it becomes blue, and then it becomes violet and ultraviolet eventually. Now, obviously, this is not a 2-scale diagram in any way, shape, or form. The wavelengths are completely wrong here for colors of visible light by orders and orders of magnitude. I understand that. I just wanted to show you a graphic so that you could understand conceptually that as the period, if you like, between the swings of the photon field between positive and negative at that point in space, the rate at which that swings, the frequency of that sine wave, that's the thing that's being used here as the measurement of the energy contained in that photon. And as you can see, as this beam of light approaches the Earth from some distance away from the Earth, its wavelength is shortened up as it approaches. It's moving at a constant speed left to right, which I'm showing as a representation of the speed of light. It's way too slow, obviously, to be the actual speed of light. So as I say, none of this is to scale, so don't send me messages saying it's all out of scale. I know, I want you to understand the concept. So what on Earth, and some distance away from Earth, is happening here? You're glad I got that one out of your yellow turd? You thought that was pretty crap, didn't you? Yeah, well, I'm not going to let you do the jokes because your language is appalling. All right, so you sit down over there. Good. Right, so that's yellow turd sorted out for now. Anyway, what is happening? Well, as you sink down into a gravitational well, such as one created by a massive object like, the Earth, the closer you get to the surface of the Earth, the slower it is for you that time ticks by. For a discussion on this, see my other fine video called What is Gravity? Where I talk about how it is that time is not constant at all points in the universe and how mass drags on time and slows it down, basically. So what we thereby see is that from the point of view of the person standing on the surface of the Earth, they will see this incoming beam of light, this photon, they would see it as being in the violet range as we see it. They would see an incoming beam of violet light. Someone else who is out in space, out about here, now would see a green beam of light going past them. Someone further back here would see a red beam of light going past them. Someone here would see an orange, yellow, depending exactly where they are. That is what they would see from their point of view. Okay, so from the point of view of the photon itself, if you were in the frame of reference of the photon, if you were able to ride along with the photon, which is impossible entirely because you have mass, which is a function of your inertia. The photon could be considered to be outside of time. It doesn't, well, some people say it has infinite inertia because it never changes its rate of movement, which is wrong, and it has no inertia at all. Unless you then want to talk about, well, how does it then cause momentum to occur and things that it interacts with? Panic until you remember that it's okay. It's all solved by the fact that mass is not conserved. Mass, there's nothing magic about mass. There's nothing about mass that confers reality and the lack of mass that removes reality and the effects that things can have on other things by interacting with them. They don't need to be physical things. So there you have it in terms of that. Of course, this is also a vast exaggeration of the exact change in wavelength of an incoming photon that you would see. I'm showing something that goes from red to violet in the course of a space between the Earth and where it's come from at that wavelength. The actual red shifts that scientists are talking about are actually much smaller than this. They're much more subtle changes in exact wavelengths that are being monitored and spoken about by these people. I'm showing you this for a concept. It's a vast exaggeration of what you're likely to see, unless the Earth, of course, was much, much more massive than it really is, had a much deeper gravity well, was able to add that much more energy to an incoming photon in the form of increasing its rate of swinging between positive and negative. But hang on, isn't space and time distorted by the gravity well? So actually, is anything really happening to the photon? Well, my answer to that is it can't be happening to the photon because, well, let me show you this Minkowski diagram thing again. Okay, so here is the Minkowski diagram where what I've done today just for fun is I've put a marker here at 4.2 light years distant from us in space-time. Where's that? Alpha Centauri, just for fun, why not? And from my point of view, 4.25 light years away. It would take me 4.2 light years to travel there at the speed of light, but given that that's not possible, I can only travel at a given variable portion of the speed of light, which changes those time and space axes as per how fast I travel. And what you'll see is that if I'm traveling at 0.01 of light speed, basically the gamma factor is 1 and the distance is still going to be 4.2 light years. Yeah, how long will it take me to get there? Well, I would need to wait for that blue arrow to be separate at that very small angle from the black one for long enough that we get that far away from the axis. So that's going to take a very, very long time to get there. If, however, I was able to travel at, say, half the speed of light, 0.5, there we go, near enough. Then the gamma factor is 1.15. So from my point of view, traveling in a spacecraft at half the speed of light, it's actually going to take me not so long at all to get there. It's going to take me 2.5 years or so, 2.5. Not 4.25. And the distance is going to be 2.5, 2.4 it says there. There you go, I was doing it visually. 2.4 is the distance in light years, and that's the time it's going to take me. So space and time changes according to my movement through space and time, my velocity vector. So what's actually happening is the space between me and Alpha Centauri is being truncated somewhat. The actual space and time between those two events in space-time is squashed by me tearing through it at a huge rate of knots. Okay. If I get to the point where I'm, say, 94% the speed of light, then it's going to take me 0.7 years to get there, and I'm going to perceive that distance to be 0.7 light years. Just by my tearing through the universe at that speed. Okay. If I'm a photon, what speed am I traveling? The speed of light. Why? Because Maxwell's field equations demand it. And that's what we observe. And it works every time we observe it. So it must be right. Okay. But what happens? Well, let's have a look at what happens to the time and the distance. It's gone. If you move at the speed of light, you experience no time. And there is no space. It's an instant connection between two events in space and time. The only thing that different viewers will disagree on is how far that distance is and how long it took to get there, depending on your frame of reference within that space-time. If you're a photon, no time at all and no space at all. There. Finished. That's why when we say we look at light from millions of light years away, we are looking into the past, millions of years ago. Fascinating, isn't it? Interesting stuff. So we need to keep that in mind because this photon started red and it ends up violet. Its energy has changed. However, the instant it left wherever it came from and the instant that it got to where it was going, from its point of view, was the same instant. Nothing can possibly have changed because change requires time in order to occur. So it's only a perception that has changed about how much energy there is in that light beam. I hope that makes some kind of sense. And the thing that changes the perception is the rate at which time is flowing locally in that frame of reference, and therefore, as a function of that in four-dimensional space-time, what the physical dimensions of space are all around us, because that's truncated or stretched out as well. Okay, so moving on from there to the pièce de résistance of this trietsy, I guess, into gravitational red shift, is that there is no reason for us to imagine that a light beam emitted from Earth, as you can just start to see now, moving away into space as a function of crawling out of that gravitational well and losing all the energy, is changing. It's now green, moving towards yellow. It's now yellow, and it will soon become orange, and then it will turn red as it climbs away from us and moves back towards where it's going to be received at the other end. So what we're saying is when we receive photons of light emanating from, say, for example, stars and galaxies and things a great deal of distance away from us, or not, as the case may be actually, the gravity that those light beams have to climb out of redshifts those light beams or photons, but whether they be visible or not. Basically, to say redshift means to elongate the wave, to lower its energy as perceived at that point in space, actually. And its energy is variable throughout its flight path, which actually doesn't occur because the photon makes that connection between those 2 points instantaneously. I hope that's fairly clear. What I'm also saying is what other sensible scientists are saying about this, which is, unless you can accurately, absolutely put a gauge on that gravity well that photon has had to climb out of in the first instance, you then might have some difficulty in partitioning the exact degree of redshift that is attributable to gravity from that which is attributable to the Doppler effect, i.e. the supposed vast and accelerating expansion of the universe around us at large. Interesting topic. Let me know your thoughts on it. Anything that wasn't clear to you from this video, please do comment underneath, ask questions. If I don't know the answers, I'll go and get them for you. But yes, I hope this has increased your understanding of the universe just a little bit today. So there you go. Gravitational redshift, a real difficulty for those who want to model an expanding universe. I'm not saying they're wrong, and I'm not saying they haven't done it. I'm just asking the question. Those of you who are really expert in the field, do feel free to comment. And those of you who are less gifted intellectually can also comment below and say that gravity isn't real and it's not a force and the Earth is flat and anything else you like too. That'll be great. All right, so thank you for your input, and we'll see you next week for another class. Yes, we will. Hope you enjoyed it. See you later.